we discussed the Newton's laws. So then what is remaining is about the mass and weight. Okay. Now, mass and weight, are they the same or different? What do you think? How? Give me a second. Right. So then, what is meant by mass and what is meant by weight? What do you think? Any guesses? Yeah. Hmm. Right. So mass means yes. Now, if you take a certain object, right, let's say pencil or something, right? So then how much matter in it, right? So now if you take this pencil to the sun or to the not the sun, the moon or the Mars or Venus, right? So wherever you took this pencil, right? So amount of material in it, right? Now you know pencil is made out of carbon, and there's a wood, there are some paints there, right? So maybe a small piece of eraser on the back, right? So then everything, they are all the material, right? So then how much amount of material is there? It won't be changing, right? Isn't it? Wherever you take the pencil, right? So the same amount of material will be there always, right? So that amount of material, right? So we can say amount of matter, amount of material is what we call as the mass of the object. Okay, so then this is what we measure using kilogram. The measuring unit of the mass is kilogram. And weight means if you keep the, now let's say you take a pencil or a certain any object on the, maybe on your hand, right? So then if you release the object, what happens is it falls down, right? So if you keep the pencil like this and if you release it, what will happen? It will fall down. Why is it falling down? Because of the gravitational force acting on this, it will be pulled downwards, isn't it? Okay, so then how much of, yeah, how much of gravitational pull or how much of gravitational force acting on this object is what we call as the weight of the object. Clear? Simply that means the mass means amount of material. So then weight means amount of gravitational force acting on a certain mass, right? Now this force, now you know when you go from different planets to planet, this value will be changing, right? If you know, you may have heard or seen videos, right? When you, if you go to the moon, right? So the your weight is about one sixth of our current weight, right? If your weight is, let's say whatever the value, right? So then when you go to the earth, your weight will be lesser, but you are taking the same amount of material, same amount of muscle, same amount of bones. So then amount of material is same, only difference is how much gravitational pull acting on you, how much gravitational pulling force is acting on you, that value will be changing. Okay, so and if you go for like, I think about Jupiter, right? So the gravitational pull acting on is much higher. It's more than twice the value acting on the Earth, right? So simply, weight means it's a force. Mass means it's amount of material. Understood? So I think that one is measured mentioned in the notes as well, right? So mass of an object is the measurement of how much amount of matter or material, right? So just this, you can say material or matter. That's a typing mistake there. And the mass is measured with kilogram, right? But if you take the weight, weight is the gravitational force acting on an object that has a mass. So then it's a force which is measured in a Newton, right? And one more thing you can say about the mass, right? So mass is a scalar quantity, right? But the weight of object is a vector quantity. Okay, mention those two, right? Now, when it comes to this mass and weight, right? So there is a connection between those. There is a relationship between those, right? Now, normally, when if you want to measure, you say, right? So we measure our weight, right? When you go to a doctor or hospital or with something else, right? If you stand on an object, right? I mean, like a balance or a scale, right? So when you stand on a balance, right, so there is some sort of a pointing scale is there, right? So when you are standing on this, right, it will point a value, right? Now normally what you say is we measure the weight. What is your weight? Someone say 50 kilogram, right? But actually 50 kilogram means it's not the weight, it is the mass of your body or whatever the object that we are measuring, right? Now let's say when someone says bring a 1 kilogram of sugar, right? 1 kilogram means it is not the weight of the object, it is the mass of that object, right? Now they are relatable, right? So they both mass and the weight means they are connected to each other. There's a good relationship between those two, right? So that relationship we write it like this: weight of the object equals mass multiplied by gravitational field strength. Gravitational field strength, right? You can write this as the equation weight equals mg. What is meant by gravitational field strength is like this. Now we know earth. Now if this is the earth, right? So we know if you have an object, so it will be attracted towards this earth, right? But we know if you keep an object near much beyond from the solar system, right? So that object will not be attracted towards the earth, and so it only attracting the objects within a certain distance, right? So that distance what we call as normally a gravitational field. Gravitational field, is this term understood? What is meant by gravitational field? Yeah. So then if you take this gravitational field, right? So now how strong is the gravitational field at a certain point is what we call as gravitational field strength. So then the strength of this, how strong is this gravitational field, right? So that is what we call as the gravitational field strength. Understood? Now this is measured like this. Now let's say you take 1 kilogram of mass, anything. It could be 1 kilogram of sugar or a book or a stone, anything, right? So then if you take this 1 kilogram of object, now we are near the earth's surface, right? Now the force acting on this, that means the gravitational force acting on this mass is what we call as the gravitational field strength at that point. Normally near the earth's surface, if you keep like 1 kilogram object on your hand, let's say you keep the 1 kilogram object on your hand, the force experiencing by your hand is 9.8 newtons, right? So we normally round it off to 10 newtons when you do our calculations, right? So that means if you keep 1 kilogram of your any object on your hand, whatever the force that you can feel, the object is pulling downward, that force is roughly about 10 newtons, right? So then if you take this kilogram object to the, let's say, the NASA space station, right? So then that value will be much smaller, right? So then it will be less than 10 newtons, right? I'm not sure exactly what is the value, right? So it will be something less, right? Now if you take this same 1 kilogram object on the moon surface, right? So then the force acting on this object will be 1.6 kilogram, sorry, newtons roughly. Okay. So then this value is what we call as the gravitational field strength. Understood? Right. So then if you go back to the note, right? So this what is meant by g is mentioned here, right? So we write the equation there, right? So here first write like this: weight equals mass multiplied by gravitational field strength. So write as equation w equals mg. So if you are given the mass of a certain object, so this is how we calculate the weight of the object. And keep in mind, mass is always measured in kilograms, the weight is always measured in newtons. So then the gravitational field strength, the unit is newtons per kilogram, that is mentioned later. So it is newtons per kilogram, value is always 10 near the earth, right? So we don't mention the 10 there, just newtons per kilogram. Okay, we're still writing, right? So then here I have mentioned the gravitational field strength is the force that acts on 1 kilogram of mass, right? So it measures the strength of a gravitational field at point. So then strength of the Earth's gravitational field means Earth's gravitational field near the Earth's surface is 9.8 newtons per kilogram. It is also known as the acceleration of free fall, right? So then the units newtons kilogram, that is also equal to acceleration unit, right? So how this one is coming is, right? So you can prove that like this. Now you know last time we learned F equals ma equation, right? So then force is newtons, then this should be equal to mass is in kilograms, acceleration is meters per second square, right? So then according to that equation, F equals mg, so then g is equal to force divided by m. So then force is measured with newtons, per newtons divided by mass is with kilograms. So the newtons we can write this way also, then kg ms squared divided by kg. So the kg to cancel out. So we get the units of the g as meters per second square as well, right? So therefore we can write the units of g as either in newtons per kilogram, or sometimes it can be written as meters per second square. Okay, right, here itself mention it, right? So we are rounding this off to 10 newtons per kilogram. Normally in the paper they say this thing, right? So take the g value as 10, they normally mention this on the paper, therefore always take it as 10. Okay. The symbol, normally we write equal like this, no? Right. So if you write like this, the first part has like a curl, so that means it is almost equal. This means almost equal, right? So this sign is equal. This means almost equal. 9.8. It's almost equal to 10. Clear? Right. So when you're doing the calculation, we take it as 10, right? And here the last point it says the value of g decreases when moving away from the Earth. Also, it will be different value on a different planet, right? Now, for example, it says on Moon, G value is 1.16 newtons per kilogram. But remember, this one you don't have to memorize the value on Moon. You only need to know memorize the value on Earth. Okay, right. So let's see how we apply this one in a question. Uh, right, write this question. Now this is simple. You just have to apply the equation, right? Now on Earth or Moon, it is weight equals mg, right? So then mass, wherever you go, it is the same object. So therefore, the mass won't be changing, right? So the mass on Earth is 25 and g is 10. So then the answer you should be getting as 25, 250 newtons. Is it? Did you get 250? Right. Then second part, again the same equation, W equals mg. The mass is again same and times the g is 1.6. So then what is this answer? 1.6 is 40, no? 40 newtons. Clear, right? Okay, we'll try another one. Uh, write this also. Rover, they say lunar rover, Mars rover, like a spaceship. You heard about the term, right? Mars rover? Those. Now they send like spaceships to observe the Mars. So then they land on the Mars and they are going all over everywhere on the Mars surface. That kind of object is normally called as Mars rover. The ones we send into the moon, they are known as like a lunar rover or moon rover, like that. It's like a small vehicle where it can detect whatever they are used for scientific researches and everything on other planets. Okay, right. You the first one. So then you are given the weight on the mass. So then if you apply weight equals mg, so weight is now 9 to 50 equals mass into g. Now this is on mass. So therefore the g is 3.7. So then what will you get as the mass? Yeah, 2500 kilogram, right? So then if you apply the same equation on on Earth, so then we can find mass is 2500 times 10 is 25,000 newtons. Clear, right? Right. I think this part is understood about the weight and mass. Okay. Right. So then keep in mind normally sometimes they will ask the mass and sometimes they will ask you for the weight of an object, but mainly you will be needing this part during the calculation, a step when you are doing a calculation, a certain middle step. Okay, right. So then I think we can go for the next section of the lesson, right? So the next one is friction. Okay, right. So at the beginning of this forces lesson, I think I barely mentioned you about what is friction, right? What is friction? Here itself it says that friction is the opposing force to the motion when an object moves against another surface. Right? Now the friction to act, right? So this is a required, right? So one object moves against another surface. That means object moved against another surface, such as when you're pulling an object along along the ground, right? So if an object is pulled along the table surface, like that, during whatever the surface, so then whatever the force acting opposite to the motion is what we call as the friction. Okay. Now mainly this friction, right? So we discuss about the friction with this next part. So that is friction and driving of the car driving car safety, right? Right, so first we'll read this point. Right, so in order to bring a moving car to rest, the brakes must be applied over a certain distance, known as the braking distance. The thinking distance is the distance traveled while the driver is reacting before applying the brakes. Right, now let's say at the beginning of this lesson, I mean during this process also we discussed the friction is a helpful thing, right? So normally friction sometimes when if you're pulling an object, so it will be a problem, but generally friction helps us, right? Now when you're walking or if you are moving, let's say when you're driving a vehicle, the friction is always helps us, right? If it wasn't for the friction, the tires won't move. That means the vehicle will not be able to move. Okay. Now let's say we have a vehicle, car or any vehicle is driving, right? So then when the car is moving forward, right? So suddenly a person jumps, or the driver of this car sees some sort of a hazard on the road, right? Let's say a tree fell into the road, right? So then what do you have to do? So the driver has to stop the car, right? So from the moment the driver sees this whatever the obstacle, until he bring this car to rest, how far the car will travel, that distance is known as stopping distance. Is it clear? As soon as driver sees this whatever the obstacle, whether the light turns red, whether a person crossing the road, right, or else something is fallen to the road, whatever happens, right? So then how far it will travel until the car completely coming to stop, that is known as the stopping distance. That's understood, right? Right. So then this stopping distance is consisting of two main parts. So one is known as thinking distance. Thinking distance. The other part is known as braking distance. Okay. So then thinking distance means, right, now the driver sees this hazard, right? Now when a person sees something, right, so he might not act on it instantly, right? So then that means, we know sometimes even when you, let's say you see something is falling, a glass on the table or something, right? So then you put your hands to catch it, but you may not be able to do it because you don't put your hand forward as soon as it starts to fall down, right? That is because of our reaction time, right? So that means the driver sees this thing, right? So it might take maybe like a half a second or 1 second to process the thought that oh, there's a road, something on the road, so then I have to stop the vehicle, right? So during that processing time, the thinking time or the reaction time, the vehicle will be moving a certain distance. So that distance is what we call as the thinking distance. Is it clear? Right. So thinking distance means the distance traveled during driver's reaction time, right? So now let's say he has decided, now okay, I have to apply the brake, so then he pushed that brake pedal, right? So he pushed this brake pedal, so then we know if you are moving in a vehicle, as soon as you apply the brakes, the my vehicle may not stop. So that means it will travel another few distance, because we know applying the brakes means you are applying an opposite force to the car's motion. So that means it is like a opposite force, just like whatever the force is acting opposite to motion. So then first it will decelerate, right? Let's say you are moving at the 40 kilometers power speed, So then it will decelerate and it will come to stop at some point. So then this deceleration, during that time the vehicle will move a certain distance again, right? So then how far it will be moving, that is known as the braking distance. So since the moment you apply the brake until the car comes to rest, how far the object is moving, that is known as the braking distance. Is it clear? Right. This one we can write a braking distance means since applying the brake, how far the car moves until it stops, right? So that is known as braking distance, right? So when you combine these two together, thinking distance and braking distance both, we call it as the stopping distance, right? Now when it comes to this thinking distance, what do you think the factors that could be affecting this thinking distance? What are the things that affecting this thinking distance? Any idea? True, right? So now let's say the speed of the object, right? Now let's say the driver takes 1 second to think, right? So since the moment he sees that road tree on the road until he applies the brake, he takes 1 second during his reaction time. So then during this reaction time, if if the vehicle is moving faster, so then during that 1 second, the car moves a longer distance, right? So therefore, the speed is affecting the thinking distance. What else? Yeah, reaction time. Yes, that is what depending on this one. What are the things that could be affecting the reaction time? I'll give you one. Tiredness of the driver, right? Let's say the driver is so sleepy, right? So we know when you're sleeping, right, we don't act actively. We don't know what. Sometimes we don't know what we are doing, right? So sometimes happen to me during these classes as well, right? Right. So then that means if the driver feels sleepy, right? So his thoughts may not act much faster, right? Isn't it? So that might cause the thinking distance to increase. Anything else? No, brakes affecting the braking distance, right? Now this is mainly depending on the driver's condition and the speed, right? Now, for example, another one, right? We can say the alcohol consumption, alcohol or drug consumption by the driver, right? So this also can affect the thinking distance of the driver, okay? And the visibility of the road, yeah, some sort of, yeah, mental stability or mental status, right? Now if the driver is angry with his wife, so then he may not see what is happening, right? So then mental status of the driver, right? So then if you want to now, sometimes they say leave your problems at home when you are driving, right? So that is because if you're angry with somebody, right, or at the boss of your office, so then that driver may not thinking straight. So he is thinking about that whatever the problem he has, so then he might face a accident. So then mental status, visibility of the road now during a rainy day, right? So then if he can't see this thing, right, so then he may not, there may not be enough time to think, right? So then he may not know what is happening. So then that also affect the thinking distance. Okay, right. What are the things that could affect the other one, the braking distance? Yeah, factors affecting, right, the conditions of the brake, right? When you say brakes, conditions of the brake, conditions, right? So then if the brakes are working properly, if they are very good, So then the when you apply the brakes, it will come car will come to rest very quickly. So that means it will reduce the braking distance, right? But if the brakes are not working properly, they are old, they are worn, so then it will not be able to stop the vehicle. What else? Exactly. Road condition, that means if the road is wet or dry or sand is there. So we know during the rainy days there are a lot of accidents happening if you go along the road, right? You will see a lot of accidents during the rainy days, right? That is because the roads are more slippery. So that means there will be less frictional forces. So then the road conditions, yes, right? Such as wet, dry, or even icy in like Western countries where they have winters, right? During the winter, they have ice. Ice has a very low friction, so which will lead to more accidents. Something else? Anything? Exactly. Tires, right? So they say you have to use new tires. Tires means with those tread marks. If the tread marks are worn, so then it will not give a proper grip on the road, right? Yeah. Conditions of tire. Right. Another one important one which is mentioned in the other side as well. There is one condition affecting both thinking and braking distances. No. Now you have once you apply the brake, so then the tiredness is no longer matters. What about the speed of the car? Right. So next one is the speed, right? We know if you move faster, right? So then if you apply the brakes, you will more distance before coming to rest. But if you're moving slowly, maybe as soon as you press that brake pedal, right? So the vehicle may come to rest. All right. So then these are the things that will be affecting the thinking distance and braking distance. Right. So you need to mention this on the note here. Right. First of all, right, so here it says the friction and drive in the car safety. In order to bring a moving car to rest, the brakes must be applied over a certain distance known as the braking distance. The thinking distance is the distance traveled by the driver is reacting before the applying the brakes. So then thinking distance has to be added to the braking distance to obtain overall stopping distance. Here after that, right, the stopping distance equals thinking distance, braking distance. Right. So then next page for the braking distance, write this definition, the one we wrote there. Uh, this one, since applying the brakes, how far the car move until it stops, and then mention the factors affecting the braking distance as well. Right. So the next side you have then you have thinking distance. For the thinking distance, right? So distance traveled during driver's reaction time, driver's reaction time, and the factors affecting this thinking distance is speed, tiredness of the driver, alcohol or drug consumption, visibility of the road, and the mental status. Right, copy this down and give me a minute. We'll do a small question. Normally this kind of questions can be related to the motion, right? So motion graphs and everything, right? Like this. Okay, we'll do this question, right? So Now this is a velocity time graph, right? So then the thinking distance means the distance traveled during this first second, right? The reaction time is 1 second. So then during this 1 second, I will use a different color. So then during this 1 second, how far the car has moved. So then that distance we can get. Yes. So yeah, that is the this area below the graph, right? Okay, so then this height is 5, the width is 1. So then thinking distance is 5 into 1, that means 5 meters, not meters per second. The distance is given in meters. Okay, right. Next one, calculate the braking distance. How do you find that? Mm, no. Now we can see he applies the brakes at 1. So then this is the point where he applied the brake. So then this is the point where the vehicle comes to rest. So during this time you can see the speed has slowly decreased. So then during this period the car will travel a distance equal to this area, right? The one I colored in purple, right? The car will be traveling that distance, isn't it? Yeah. So then this distance is equal to the braking distance, right? So braking distance, you can see once the brakes are applied only, the speed is decreasing. Then how far the vehicle is moving during this period. So that is what we call as the braking distance, right? Okay. What is that value? Tell me. You see, no. So then this is triangle. So then area of the triangle is half into base into height. So then base is from here to here, right? How much is that? Base is 5, right? 1 to 6. So then 6 minus 1 is 5. So then height is also 5. So then it is half into 5 into 5, right? So that means I think 12.5 meters. Clear? Right. So then what is the overall stopping distance? No. Stopping distance means what? Stopping distance is equal to, here we wrote stopping distance is equal to thinking distance plus the braking distance, right? So then, no. What do you get? So then, thinking distance we got it as 5. So now we got the braking distance as 12.5. So then, stopping distance is, so thinking distance plus the braking distance. The thinking distance is 5, braking distance is 12.5, that is 17.5 meters. Okay, right. Uh, and I will share another PDF with you on the group, right? So that contains some questions, right? You can try that one later in your home, right? So now you can do most of the question except one or two. Right? So let me share it before I forget. So even the first question I gave you is also from that same PDF, right? So you can try those questions at home, right? And if necessary, right, we can try some questions later, right? Let me find another one. Right now, you can see this is almost the same question that I gave you, right? So this is from, again from a past paper, right? So this is similar to the one we did, right? Only the values are different. Okay. So then this is the question we did earlier. Right. Try this question. Driver can car sees an obstruction on the road ahead and must stop the car. You try for this one. Right. Uh, First one. Yeah. Okay. The next one, car travels 21 meters per second. The driver's reaction time is 0.14 seconds. Calculate the distance traveled by the car during this driver's reaction time. Let's see. 2.94, yeah. So then speed is distance divided by time. So then distance is speed into time. So then speed is how much? 21 multiplied by 0.14. This is giving you the answer as 2.94 meters. Right. Right. So there's more to this question, this part. Yeah.